Alrighty. So let's double check this computer audio. It says I'm talking, so that must be right. Okay. Now let's all right. Well, we are the few, the proud, and I don't see that there are a lot of folks joining us in via Zoom, so I'm a little disappointed. And I guess I know at least one team is one team is not here because they're meeting with Dr. Morgan. So the first thing that I wanted to do is kind of run by where I can look in people's eyes and make sure that everything that we talked about last week still makes sense today. Or not, I say last week, on Monday. And that is semaphores. So first of all, let me ask you guys something. Does the train analogy help you guys understand what we're talking about here with semaphores? And one of the key aspects of semaphores is understanding the use between something being available, not available, versus something being an event having occurred. So in one sense, the available, not available is almost kind of an opposite logical polarity from hey, an event has occurred. So at least when you start off. So the idea is that when you create a semaphore that is to block something, the assumption generally is that the availability of that something when I create the semaphore has occurred. That it is, when I first initialize the semaphore, that whatever it is that I'm talking about is available. Okay, so in that sense, we always want it to start off in the available state, which is not equal to 0. In the case of a binary semaphore, not equal to 0 also means 1. And that's another thing that you need to kind of keep in mind, is that not every operating system, if they know that you've got a binary semaphore, does a great job of making sure that it can't increment beyond 1. That when you do its thing, when you post to it, it goes to 1, and if you post it to it again, it doesn't post it anymore. But it's really important to understand that distinction, because you can get some really weird behavior if you create a counting semaphore, but your intent was to treat it as a binary semaphore. Because obviously, if more than one task posts to it, then now you have to have more than one task pinned on it before anybody can do anything with it. How about wait forever, no wait versus timeouts? Does that concept make sense to you guys?
What's the difference between wait forever and no wait?
Okay, big difference. So wait forever, if I pinned on a semaphore and I say wait forever, then the only reason that that function will ever return to my task is if someone posts that semaphore. Okay? If I say no wait, then the pinned is not really pending. It doesn't stop. So if the semaphore is available, then it will decrement it with no wait. It will decrement it and move forward just like it would if you had wait forever or you had a timeout. If, on the other hand, that semaphore hasn't been posted, it simply returns still, but it's going to give you an error return code that lets you know that that semaphore wasn't posted. So this would be a time when you want to you want to use the semaphore, but if the semaphore is not available, you have something immediately that you want to do in reaction to the fact the semaphore is not available, as opposed to waiting for a timeout. So it's effectively a timeout of 0. Okay, and in fact, if you take a look at the way the OS has created these, since it goes in that timeout field, if you take a look at the way the OS has implemented it, BIOS no wait is 0. It's just defined as 0, and BIOS wait forever is all Fs. It's the maximum value that it can take on. So it's probably too early for you to understand the import in terms of, you know, actually having seen the way kernels work and that sort of thing. The import of this TI oddity. What is important is that when you set up in your kernel, unless you have an amazingly good excuse, you always want to use the underscore priority version of the semaphore type. So did this animation help you guys when we went through that? Okay. All right. So for semaphore calls, there they are. It's one of the nice things about the TI kernel. So I gripe about TI tools from time to time, but there are some good things about it. And one of the nice things I think about the TI tool is that when you want to figure out how to use a particular piece of the kernel, the pattern is always the same. There's always the whatever element it is, param init, to get some sort of a structure set up. There's always a whatever it is construct to actually tell the operating system, here you need to put this aside, this is the information that you need to have, and we're going to operate with this and get started and registered with the operating system. That's always the same. Handle is there for most things that have a handle where you're going to be referencing it otherwise. And so you get this, and they always have, and their terminology about pinned and post is always consistent. So the fact that it's consistent really does, as we start adding on more stuff to our repertoire of kernel calls, this is really going to help make it a little bit more straightforward to kind of figure out what's going on. You can pretty much assume that if you're doing anything with TI kernel, that somewhere you're going to have a param init call, and somewhere you're going to have a construct call before you actually use whatever elements you're going to be using. And deadlocks, that's one of those things. I've tried to explain deadlocks 100 different ways. And I always feel like that after I explain it, I'm confused. Because it is not a super easy concept to get in your head, but it is a really easy thing to break. And so it's one of those things that you kind of need to watch out for, whether you're dealing with semaphores or you're dealing with what we're going to talk about next week, mailboxes, or any of those other things. The order in which you pinned on things always makes a difference in an operating system. And there's nothing you can do about it other than discipline. Okay, there's nobody who's going to enforce upon you that rigid structure. Cool. So let me ask, did anybody have any problems with this second homework assignment where we were doing the timer-based version of this in an RTOS?
So I know in the homework you said to use the sysdig module. Did you mean use like the way we had it in the first one, which you use like time period?
So what I was referring to was that you have to set. I wanted you to set the time period to something other than the default, to 5 milliseconds on sysdig rather than the default 1 millisecond. In terms of using, in terms of achieving your time delay, and I know I've included this call in the thing, I wanted to use task sleep to achieve your timing. But yeah, that task sleep uses systic to figure out how long it's going to sleep. So what you're passing to task sleep is a number of timer ticks. It's not a time. It's a number of how many times we hit that systic element. Does that help?
Yeah, that's what I assumed it was doing. It was just more of like you had asked for systic, and I was like, I didn't set up systic module like I did in the first one.
Yeah, you don't have to explicitly call that. The operating system takes care of all of that for you.
Okay. Then yeah, no. Then.
Okay, good. Any other things? Well, let me show you my solution. And first thing that I want to do, and we're going to talk about these in a minute, but I want to this is, so you guys saw last week the 2-page flowchart that I did for the first assignment. The second assignment, and I actually made this a little simpler than I normally would, but the fact is that what I want to convey is that when we're working with a kernel, because the kernel does so much of the work for us, it's actually much easier to express what our design intent is and to make sure that we're covering our design intent without having to go through every if, and, or but in a detailed flowchart. So let me zoom in here a little bit. So, and I'm going to talk to you a little bit today about how you express things for operating systems. But this green symbol is my RGB blink task. It's the task that I created to do all the LED blinking. This task sleep here just represents this particular task is going to utilize that function, that operating system function that is a timer element. And I also have here, this is a hardware interface. This also is going to actually talk to the hardware. And then I have this note here that there are actually going to be 3 instances. So I could actually have drawn this instead of putting a box around it and saying that there are 3 instances with different delays and different color LEDs. I could have, if I'd wanted to, actually just repeat this block 3 different times and put the information in the task description about which color it was. So if you take a look at what my main function is, the main function consists of initialize the board with general I/O and initialize it using the iNet GPIO. Those are the 2 initialization calls you have to make that are part of the BSP. You construct the tasks, and you start the RTOS. And I don't have to draw an exit out of this particular piece of the flowchart, nor do I have to do a loop, because I don't loop. I actually start the RTOS, and then the code that I was executing in main is no longer a factor at all in the operation of the system. So in effect, your program ends after you start the RTOS, and now everything is in control of the RTOS. And then this is my RGB blink task, and it's highly complex, okay? You guys need to pay very close attention to this flowchart to make sure you understand it exactly. I start off turning off the LED because that's the state that I want everything to start in. Could have just let it come up randomly, but I like to explicitly turn it off. Then I toggle the state of the LED, and then I sleep. And after that, I toggle the state of the LED, and I sleep. That's a great way to write code, right? It doesn't do anything. This is a while one loop, and you're done. And that's the way most operating system stuff, when we break it down to its fundamental pieces, is going to work. So let's go take a look at what it actually took to implement that. Yes. Okay. So I'm going to, I think I got more than one thing working on. I got impatient. I think I got more than one thing working on this deal. But I'm going to go back over here to take a look at my Blinky kernel code. Now, one of the things that I do, it's not required. I encourage you to do this, though. If you take a look at how I have broken this up, you'll note that I have this C program called blinkKernel.c, and that contains my main. Okay, and then I have a separate function called RGB blink task, and that's where I put my RGB blink task. So I like to break up into different source files things that can be logically isolated from one another. It makes debugging a whole lot easier because I don't have to go running through hundreds of lines when things get complex in source code to figure out where stuff is. So let's start off with the RGB blink task so that you can see what I did there. Let's load him up. And the other thing that I want to do is that I have this include file that I have made, and I want to get him open too. Okay. So let's talk a little bit. We're also going to talk a little bit about coding standards here as you're looking at my code so that you can kind of see what's going on. So up here at the beginning of every file, there is this header that announces basically why you generated this particular file, who you are, has the file name, and then a very brief description of what's in there. The other thing, have you guys ever seen somebody doing this in a header file where you have this pound if indef, pound define indef, and enclose all the stuff in the header file in that? Have any of you guys ever seen that? Who has not seen that? Does anybody want to venture a guess as to why we put that into header files? So no, good guess, but no. So one of the things that happens when we have really complex programs, so this is not a very complex program, but if you take a look, you know, here we've already got 4 includes, right? And it is not uncommon to put includes and other includes so that something that you've declared is always going to be declared properly. So as a, for instance, I might choose to put std and include stdint inside an include file so that whoever is using that include file doesn't have to think about including stdint, that it's just there. The problem, of course, is that when the compiler sees that same code included twice, the compiler will barf, which is a technical term for generate an error message. Okay? We don't want the compiler to barf, obviously. So what we do is that we put, these are called sentinels. And the reason they're called sentinels is that the first time I include this RGB task.h, this variable right here that I have named basically after the file name, right? That variable is going to be undefined. So we're going to go through and we're going to include all of the junk that's in here, right? Well, the first thing that I do is that I pound define that thing that was undefined when I got in there. So now I can include RGB blink task.h a dozen different times, but the next time through, this will be defined, and so it just runs down here to the indif, and it ends up including a couple of blank lines in the file that gets actually compiled. Does that make sense? Okay. So I could have done these blink tasks a dozen different ways, but what I chose to do is that I chose to make it so that I could have this generic blink task that I would tell it, here's my LED. Oh, wait a minute, that's not the one that I wanted to show you anyway. That's let's go to 2A. I like his better. That's why I had 2 and 2A. I could not remember. This was an old piece of code. Structure has got a lot less stuff in it. That was using the first one I did was not using the OS calls or the kernel calls. It was actually using the library calls that you guys used, not this week's assignment, but previous week's assignment. So let's go to where I had defined this. So you'll notice same sorts of stuff here, but this structure is a little bit different. So this structure, this first piece of the structure is just an integer, and it's an LED number, because as you recall from what I told you guys last week about setting this up, when we set up the GPIO for the kernel, basically every IO bit gets assigned a number that has all of its parameters associated with it, including which port it is. And then when we call the kernel functions to toggle or set or reset a particular bit, we pass it that number. So I have here a spot where I can include the number that indicates which LED I want. And then I have a long int that is how long I want to delay, how often between blinks on this LED. So now my code looks like I have passed this particular function. I have passed a pointer to that structure that has the LED number and it has the time delay. And so now my code is pretty simple. I'm writing a 0 out to that particular port with a GPIO write. And then in my while loop, I'm toggling whatever the LED is, and I'm sleeping. Now let's go over to where the main is, where we get that all initialized and run through that real quick. That is in that guy right there, blink-kernel.c. Okay. So blink-kernel.c, lots of includes here. So most of this stuff is stuff that you just have to include because, hey, you're working with the kernel and you're eventually going to call some of this stuff. You'll see a lot of stuff that falls into this XDC category. And that is generally about, all the XDC stuff is generally about very low level hardware interfaces. And stuff in this TI tree, particularly TI sysbios, is a little bit higher level stuff. If you're going to use the drivers, you have to include the header file for it. And this board.h file actually is something that we created. It started off, but you can alter it. Oh, wait, no, we didn't create that. This is no. This is where you specify which of the I/O modules this board supports. So we're not modifying this time, but we might in the future go in here and say, hey, we're going to be using a different kind of a port, potentially, like an extra SPI port. Yes?
I changed that to use RGB and
So did you change it here, or did you change it in the,
I changed it there.
you changed it here?
Just LED 0.
Oh, you changed, okay, you changed these definitions. Okay, and that's perfectly okay. That's perfectly okay. So we've looked at that one. So let's take a look at what I've done. So the first thing that I did, I gave you all the hint that 512 is a dandy starting stack size for anything in this particular RTOS. It's probably overkill for the blink task. We could probably get by with something closer to 128 bytes. But keep in mind, every time an interrupt happens, something else is going on that you don't necessarily have control over. So it's always better, if you can, to allocate a little more stack than what you need. I have in the operating system initialized this thing to be 5 milliseconds between ticks. I put in this pound define so that I could make it easier for me to understand different places how I came up with numbers. So down here, my red delay, that's supposed to be 500 milliseconds, right? So I take 500, divide that by milliseconds per tick. And one of the things that you need to that you ought to be learning about C, this is a general lesson about C. Math in pound defines is always free. It costs you no compute cycles to do math in a pound define. Because when the pound define expands, it will actually take that 500 divided by whatever milliseconds per tick is, and in that case, it's going to come up with the number 100. And it will put the number 100 in the code, not the computation. Okay? That's all it happens at compile time. So in some places, you know, sometimes you start thinking, well, do I really want to do that math? Do I want to do that divide or whatever because of timing issues? You never have to worry about that if you're doing it at compile time. Now, having said that, if instead of 500, if that had been a variable, something that could change at runtime, then of course now the compiler can't figure that out, and so it can't do that divide ahead of time. But as long as everything that you're working with are constants, all the math you do there is free, and a lot of times doing the math there helps explain what you're doing as well as a comment would. I don't have to put in a comment that says 100 is the number of ticks that we're going to generate because we're doing it at 5 per tick. That's implied by what you see there. Now, I have this other pound define here that because I wanted to be really cool and be able to either blink the RGB LED on the launch pad or the one on the edu board based on what I set this to. And so down here you can see where I've created my structure where I'm initializing this structure right here, right? It's got the LED number and then the count. And so I have my red. What did I just do? I don't want that. Okay. I have does this thing recognize gestures? Oh well, not important. All right, so I have these 3 structures of LEDs that I'm creating. And if we hover over, you can actually see what values they're putting in. So LED pin 1, delay count is 100 on that one. LED 2, delay count is 80. And the LED is 4, and the delay count is 60. So it's creating those structures. Now, let's go back here to this LED task, because this is important. You'll notice that while I'm in that while loop, I am constantly referring back to that structure to get the LED number and to get the delay count, right? So if I try to reuse that structure over in my main program, use the same physical structure for each of my LEDs, they're all going to be referring back to the same number. And so whichever one we initialized last would be the one that did the blinking, and everybody else would be blinking basically in unison, because all the tasks would be working off the same data. Okay, so it's important to remember that when you are in the kernel, it's important to remember that you, in fact, have to keep around any static structures that you're passing off to your tasks. I'm going to stop here and see if there's any confused looks. Okay. All right, so let's go back to the kernel task. So we're doing that. We come down here, and initialization stuff is straightforward. We initialize a task params here that we're going to be using. And in this case, I'm going to reuse that task params every time I set one up. So here we go, task params for, this is the pointer back to that red structure that we created. Green structure, or green spec, red spec, blue spec. So here we're passing in an arg0, passing a pointer to my stack, and then I am calling this function to tell it to initialize a red task, a green task, and a blue task. And then I tell it to go, and let's just see what happens when we do that. Okay, and we tell it to run. Now, as you can see, nothing up my sleeve. Got the edge board LED blinking. And if we went back, let's stop this. And let's go back and let's change this guy to a 0 and recompile. Whatever. Nothing happens fast. That would make it too easy. Now, again, nothing up my sleeve. Remove which LED it is. And the code's pretty easy to understand what we're doing. Now we're going to start talking about, as we start doing semaphores, we're going to start talking about things that are communicating from diverse areas. So it's going to start getting in. We're going to start getting to areas where it is going to be really handy to create diagrams of what we're talking about. So I want to show you guys, and all of this should, by the way, be posted as well. Oh, that's right. I can't minimize them. You told me that before. Thank you. We're going to go over here to that PowerPoint. So I want to show you guys a little bit about some documentation. So I have this lecture. I'm not going to go through the whole lecture today, but it is posted. And I'm, in fact, actually going to be doing this for giving out to the 419 classes, just doing a recording of it. And I'll let you guys have that when I'm done. But I want to go over here. It's important that you take a look at flowchart symbols and do standardized flowchart symbols at some point in your life. But I want to talk about control flow diagrams, because that's something that we use a lot in kernels. And the concept of a control flow diagram is basically we want to know how elements, it defines the flow of logic within a program, not necessarily where the program counter goes, but where the overall logic of the program is going. So the idea here is that we have symbols for the tools that we use for communications. So binary semaphore, a counting semaphore. Notice how cleverly we distinguish between a binary semaphore and a counting semaphore. A binary semaphore is just a flag, and a counting semaphore is a flag with a pound sign on it indicating a number. Okay? We're going to learn here in a couple of days about mutexes, which are a specialized kind of semaphore that are made explicitly for locking access to a particular feature within a program. And it's because it's locking, we make it a key. That's a old-fashioned key, or at least the best one that I can draw. Mailboxes and queues. So a queue is basically a thing that can hold a series of messages or values that are first in, first out. And so we draw the queue looking like, you know, kind of a stack of stuff with elements in it. And the mailbox, we ought to all recognize that particular thing, right? We'll talk eventually about event flags, but timers we've already talked about. We symbolize a timer simply with a clock. And then we have different kinds of elements that we display on this diagram. So a task, we use this rounded box with the bold outside, and that's a task. That's something that goes off and executes forever without ever stopping. Interrupt functions, that's a really crummy lightning bolt that I drew over in the top corner of that. An interrupt function is exactly that. An interrupt function is some external influence causes the interrupt function to execute. It does whatever side effects it has, and then it returns back to wherever normal operation was. And these yellow boxes are common functions. So that by common function, what I mean is printf would be a common function. What else would be a common function? The GPIO write, okay, writing to a GPIO toggle. Those are common functions. They're functions that you call and they return, okay? And we often will put those in communications diagrams because it may be the functions that we call that have the actual side effects that are operating system associated. Anytime you're talking to a hardware device, an I/O pin, or whatever, we symbolize that with a box that has a wrench in it. And global variables. So we will use global variables from time to time. And when we use global variables, we use the hexagon that we have there. And one of the things that we do on that is that I like to, it's not necessary, but I like to, because it makes it easier for me, understand the difference between where I'm only writing to a global variable from a particular location, or I'm only reading from it, or I'm both reading and writing from it at a particular location. So this is an example of a control flow diagram, and I'm going to talk to you about what this is so that you can kind of see what the idea is behind trying to draw this kind of a diagram. So this is a task that we're calling the logger task. And his job is for somebody who wants to send something that needs to be logged, is to put that information in a EEPROM that the log happened, and also to print it out to a serial port. Okay, so you guys can think of a dozen different reasons that you might want to do this in an embedded system, right? Something happens, you want to record that it happened, record it permanently in a EEPROM, send it out to serial port so whoever is there sees it, right? So here's how this particular one works. If somebody calls this send sensors to log function somewhere, I don't care where, when he gets called, he pushes whatever message it is onto this queue. Okay? And when this guy gets done with it, it puts a pointer back to whatever storage thing that we had back into the queue so that we can reuse it. So the way this is set up, there is somewhere this magic chunk of buffers that we're using for these messages. And while we're waiting for them to get printed out, we might need another one. And so this allows us to basically do that in a circle. When I send something, I'm pushing it here. When I get something, it comes back here. Now it's back in my pool. This logger task sits there, and his job is to wait for something to come in there. That's all he does. He's going to depend on this log message queue basically forever. When he sees a log message, he's going to use these functions to send it out to the EEPROM. And he's also going to send it out with a puts, sending it out to the serial port. Have a timer here because we might time out. If the double EEPROM doesn't answer quickly enough, we might want to have a timeout that says, oh, well, that's never going to happen, so let's just forget it. Okay. Obviously, right into the EEPROM. And this locked EEPROM here, that you could think of that as potentially a semaphore, but the idea here is that with that mutex, there might be other tasks that have to write stuff into the double EEPROM, right? You know, there's other things we might want to put in the double EEPROM other than just errors, okay? And so what that lock does is that lock, while this task is writing an error in there, it prevents another task from coming along and grabbing it. So what I am not going to do, so I'm going to tell you what I am going to do, what I'm not going to do. What I'm not going to do, well, when I taught the previous class, I had people working in programming teams as opposed to one individual programming. So you kind of spread the work out. And that was good because I could give more complex programs. But where it was bad was that not everybody was really understanding because not everybody was really participating in the writing of the programs. But one of the things that I did have the previous class, the last time I taught this, that I had people do is actually create these diagrams for your programs. I'm not going to require you guys to create these diagrams for the programs, although the Visio templates for all of these are posted up on eCampus so that you can if you want to. And I would suggest that as our tasks get more complicated, that even if you don't sit down with Visio and do a formal version of this, that you sit down on a piece of paper at somebody's whiteboard or whatever, sit down and design what it is that you're going to do before you actually implement it. So, having said that, I think we've covered everything that I want to cover for today. Depending on y'all's schedules, we've got technically about 15 minutes left, 10 or 15 minutes left. Is there anything that you guys want to discuss while we're sitting here? Yeah.
On your solutions for the homework, you only use one task parameter, and when I tried to do that, it gave me a heap memory variable, saying that I'm assuming I ran out of memory trying to set them up. I'm not exactly sure why, but it fixed when I changed it to create 3 individual task parameters, but then that makes 3 individual tasks. I'm not understanding this correctly.
So when you did, it was the task param structure that was your problem?
Yeah, like when you know how you do task params, like stack size, stuff like that.
Right.
I created different like stack size, and I had different like variables for them. But I did task params dot stack size, and when I did it for all 3 of them, I got like a heap memory error, and I couldn't fix it, so I just made 3 different task params.
Okay, so when I grade your code, if I see what's in there, I will definitely explain to you what you did. So let's talk about, does everybody understand what heap memory is versus stack memory? Okay. Because I have a guess, but it's just a guess. Well, let's talk about the way memory is organized in any one of these programs. So, and I'm going to go with the architecture for this particular 420 that we're using. And I'm only using the subset of RAM, okay? You do wrong, and you know, the I/O ports and all that stuff, this gets a little more nonlinear. But basically, the way that our program memory is set up is that there's this thing called a heap down here. And then there is up here the primary stack. Then below the primary stack, or excuse me, down here because they're actually variables, static variables. We have our task stacks. Okay, so when you create a global variable, it gets put down here just above heap memory. Okay. Sometimes it gets put below heap memory, but they're all basically grouped down together. So the primary stack grows this way. Each one of these stacks individually grows down inside of them. And so then you're going to have this big chunk in the middle. Now, heap memory, to use heap memory, the only way to use anything in this heap memory is to use the malloc call. Okay? Or in C++, the new call. Okay? So malloc and new, basically, in both of these cases, you're saying, hey, I need to use X number of bytes of memory, and it will pick a chunk of memory out of here and give it to you. And then there's a free, or in C++, delete call that you use to say, I'm through with this memory, you can have it back for somebody else to use. Now, if you take a look at the TI function calls, there are two ways to create both tasks and things like semaphores. So there is the construct call, which is what I put in my notes. And the construct call takes a structure that you have provided for the task control block in this case, and puts everything in that particular structure without ever having to deal with it. Okay. The create call, I think that's right. I think it's create versus construct. We'll have to look at the guide documentation. The other call, you don't pass it your task control block. Okay. What you pass it is that you pass it, you just pass it the parameters structure. And what happens is that particular function call will go out and it will do a malloc to allocate your task control block in this area. Okay? If that's what you did to create your task, then if you create the third one, there may not be enough heap allocated for all that because the default heap size, which is set up either in that the XDC GUI or in that file that we talked about, the two different ways that you can set up the timer kit. In that file, you also are setting up how big a heap you're allocating. So it's possible that you just didn't have a big enough heap allocated and you were doing the create rather than the construct or vice versa. So that's most likely, but we don't know for sure. Okay? But I will check it out and let you know. Any other questions? Comments? Am I grossly unfair? So I would, I haven't seen anybody drop in the class, and I've seen a lot of, everybody turned in their first homework. So I'm curious as to why we don't have as much attendance on Wednesday as I would expect. There's 1, 2, 3. So we got 6 folks who are absent. Yeah, we got 15 enrolled. We got 6 folks who are absent. So I'm curious if anybody knows. I'd love to know why the attendance is not great for the class. I'm boring or not helpful or whatever. By the way, on the other side of this, I love to hear myself talk. Make no mistake, I really enjoy this. Okay, I like being the expert, but if you pass all of my tests and you do all of your homework and your homework is all perfect, if I never see you, I'm perfectly okay. Okay? I get that you guys have got 100 other things, and if this is a review that you're trying to get credit for, man, I'm good. Okay. So I'm not counting attendance. I guess, but I am curious as to why attendance is like Cool. All right. Well, we're done. Party on.
When are you gonna release the latest?
Did it not get released? It did not? Well, let's take a look. That's something. Hold on a second. Let me stop Zoom. So whatever. Okay. End meeting. End meeting.